Welcome back, guys. In this video, we'll do one more example of finding a tangent plane to a surface. We will also talk about what people mean when they say they're looking for the linearization of a surface, and then we'll look at finding the normal line to a surface at a point. So this is our example. Now this is one that I don't know what it looks like. I'm not really sure what this surface looks like, but I know if there is a surface that satisfies this equation, if there's a z as a function of two variables that satisfies this equation, well, then this would be a surface in three-dimensional space, because I've got a function of x, y, and z equals 4. If I want to find the tangent plane at this point, all I need to do is find capital F, and normally we set capital F as a function of three variables. We set this equal to 0. We find its gradient, we evaluate it at that point, that's the normal vector, and once we have the normal vector and the point, we substitute those into the equation of a plane. So that's the plan, and then we'll talk about what all of this means up here. So let's do this example. This is for some surface I can't visualize. So I'm just going to draw a cartoon surface over here. This is not our surface, it's just some cartoon. Often we've got z as a function of x and y, and that generates a surface because every x, y in the domain gives us a z. Now sometimes we'll have capital F of x, y, and z equals k. That's a function of three variables, and it's just convention to use a capital letter here and a lowercase letter here. And if I set that function of three variables equal to a constant k, we get a level surface of this function of three variables. So there are two ways to represent surfaces, this way and this way, but either way we get a surface. Either z equals a function of two variables, or a function of three variables equals a constant. Now we're trying to find the tangent plane to some surface. Let's say it looks like this. It probably doesn't, but let's say it does. And we want to find the tangent plane at the point x equals -1, y equals +1, z equals -1. Okay, that's not even on my picture. Yeah, so the surface would have to be down here somewhere. Maybe that's part of this surface. Who knows what kind of crazy thing it does. It might not even be a function. You might get two z values. So maybe let's say the surface actually exists down here. X equals -1, y equals +1, and z equals -1. So we're going to go over here, and here, and then we're going to go down 1 unit. It's a little bit hard to see. Say, oh, that's our point on the surface. -1, 1, -1. And we want a little tangent plane right there. This is just a horrible, horrible picture, but I hope you get the idea. We're trying to find a tangent plane at that point, and who knows what the surface looks like, because this is definitely not one of the surfaces we studied in the other chapter. So we're given the point. We always need a point and a normal vector. We've got the point. So this is x naught, y naught, z naught. Next thing we do is we find capital F. Typically we set this equal to 0. We could also think of this as a level surface, f of x, y, and z equals 4. But just to stick with our convention, we'll set it equal to 0. And then we compute the gradient of this surface. The gradient of this function of several variables, and then we evaluate it at that point to get the normal vector to the surface. Or a normal vector. So we know the gradient is just the vector of first partials. It's a function of three variables, so we've got three components. So we just need to find those first partial derivatives. We've got x squared y cubed minus y squared z plus 2xz cubed minus 4. and I want to take the derivative of this with respect to x, treating y and z as constants. If y is a constant, that y cubed will come down. I have a constant times x squared. The derivative of a constant times x squared is that constant times the derivative of x squared, which is 2x. There are no x's here, so the whole thing is constant with respect to x, so we get 0. Then this is a constant, because z is being treated as a constant when we take a partial derivative. A constant times x. The derivative of a constant times x is just the constant. And of course, the derivative of -4 is 0 with respect to x. So that's our partial with respect to x in general. And later we're going to evaluate it at that point. Now we want to find the partial with respect to y. We'll do the same thing. Treat x and z as constants and differentiate with respect to y. Since x is a constant, I'll bring down my x squared because this is a constant times a function of y. So bring down my constant and I take the derivative of y cubed with respect to y. That's 3 times y squared. Over here I've got a constant, -z, times y squared because I'm treating my z as a constant. So I bring down my constant and I take the derivative of y squared with respect to y. So I get 2y. Here there are no y's, so this is all constant. The derivative of a constant is 0, so that's gone. And the derivative of -4 is 0, of course, that's gone. So that's our partial with respect to y. Now we want a partial with respect to z. So we'll treat x and y as constants this time and differentiate with respect to z. There are no z's here. Derivative of a constant with respect to z is 0. This is a constant times z. The derivative of a constant times z is just the constant. And this is a constant times z to some power. So you bring your constant down. And then you multiply by the derivative of z cubed. That's just 3z squared. And the derivative of -4 is, of course, 0 with respect to z. So we have -y squared plus 6xz squared. Now those are the components of our gradient vector in general. And if we want those components evaluated at -1, 1, -1, we just substitute those in over here. So the partial of f with respect to x at -1, 1, -1 is 2 times x times y cubed plus 2 times z cubed. X is -1, y is 1, z is -1. So I've got a -2 minus 1 times 2 is -2, so I get a -4 there. Okay, now we're going to take the partial of f with respect to y and evaluate it at this point. So I've got x and y here, so I replace x with -1, y with 1, and a y and a z here. I replace y with 1 and z with -1 and simplify. -1 squared is +1, so this is 3 minus 2 times -1 is +2, so we get 5. And the partial of f with respect to z evaluated at this point is this. -y squared plus 6 times x plus z squared. Y was 1, x was -1, z was -1. So I have 1 squared, which is 1, times -1, so that's -1. And this is +1 times -6 is -6, so we get a -7. So those are the components of our gradient when we evaluate it at -1, 1, -1. So we get -4 as our x component, 5 as our z component, and -7. I said as our z component, that's our y component, and this is our z component. Now you can use this as your normal vector if you want to. I like my normal vector to be made of small integers, this one is, but I like my a in the equation of my tangent plane to be positive. A lot of textbook authors do. I don't know why. It just seems nicer and cleaner to me as well. So I'm going to multiply this vector by -1 to make that a +4 instead of a -4. So you're defining the normal vector n, which can be this vector if you want it to, or you can multiply by any constant, which is just going to change either the length or the direction or both. When I multiply by -1, I get 4, -5, 7. And then I take my normal vector with components a, b, c, and the point, x naught, y naught, z naught, into the equation of a plane. And then simplify. So we've got a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And a, b, and c are right here. That's my a, that's my b, and that's my c. And x naught, y naught, z naught are right here. X naught, y naught, and z naught. So I'll just substitute. A is 4, B is -5, C is 7, and x naught, y naught, and z naught are -1. Subtracting a negative is the same as adding. +1 and -1. Subtracting a -1 is the same as adding 1. So that's our equation unsimplified. And now we'll distribute and simplify. So I have 4x plus 4 minus 5y plus 5 plus 7z plus 7 equals 0. 4 plus 5 is 9. 9 plus 7 is 16. We're going to subtract 16 from both sides. And we'll have 4x minus 5y plus 7z equals -16. And that is the equation of our tangent plane. So with my cartoon surface over here, which is so horrible looking, and I'm so sorry, I wish I actually knew what this thing looked like. My tangent plane is 4x minus 5y plus 7z equals -16. And we're done. We're done with that. Now, you might be asking yourself, okay, what is linearization? Let's talk about what linearization meant in Calculus 1, and then we'll talk about what linearization means in Calculus 3. When someone asks you for the linearization of a function in Calculus 1, all they meant was look at the graph and then find a tangent line at that point. So they couldn't just say find the linearization of the function. They'd say find the linearization at a particular point. So at x naught. So you've got some function, maybe y equals f of x, and it looks like this. And they say find me the linearization right here at that x naught. Well, all you would do is you'd find the tangent line right here. You'd solve it for y, and you'd replace y with L of x. So L of x is just going to be the equation of a line, mx plus b. And we're going to call that the linearization of the function at that point, x naught. It's just another name for the tangent line. So linearization and tangent line in Calculus 1, they are the same thing. We came up with a formula involving derivatives, and it looks very complicated, but really if you had already been calculating tangent lines, which you probably had at that point in Calculus 1, you weren't doing anything new. I just gave you this very involved looking formula to write down the tangent line, but really, linearization and tangent line are the same thing. Say, okay, well, why do they even talk about it this way then? Well, they talk about it this way because often we're interested in a linear approximation to the function at a particular value. So linearization is a term that people use, scientists use, to describe the linear approximation to a function at a point. And if in Calculus 1, what they probably said was, they said, let's say we're on our calculator and we look at our graphing window, and first it looks like this, and we see the whole thing. Like, this is what our graphing window looks like. We see this very interesting curve. It's got lots of interesting things going on. We've got hills and valleys, and we've got end behavior, and it's great. And they say, I'm not interested in that. Let's zoom in right here. What does the function look like near x naught? And so we zoom in on our calculator, and then we say, it still looks a little too interesting. We're like, what happens if we keep zooming in? And we keep zooming in, and we keep zooming in. Eventually, you're looking at your calculator screen. Let's take this guy over here. Eventually, you look at your calculator screen and you're seeing like this. I did not do a very good job with this. Here we go. So you zoom in and you see, like, here's the curve. And there's the tangent line. And they say, don't even do that. I want you to zoom in even more. Zoom in again. And eventually you get to the point where you can't even tell the difference between that line and the curve. And maybe this is the point x naught, y naught on the curve. Eventually you get to the point where the line and that curve are indistinguishable. So we kept zooming in and zooming in and zooming in and zooming in and zooming in. And we said, hey, there's some level when that curve is basically a line, basically, for all practical purposes, from our perspective. If we're this close, it looks like a line. Tell me about that line. What is that line? Well, it's just the tangent line. But we're thinking of it differently. We're thinking of that tangent line, that red line here, as a linear approximation to the function at the point. As you zoom in and zoom in and zoom in, eventually the function and the tangent line are indistinguishable. Provided that the tangent line exists, there are no sharp corners there. If there's a sharp corner over here, like let's say it's like an absolute value or something, if you've got a sharp corner or cusp over here, well, still we could keep zooming in until we didn't see the cusp anymore. If we're talking about a point where the function's differentiable, the line or the curve given by the function and the linear approximation are indistinguishable. And they're saying, what's the equation of that line? Okay, so it's usually, this word linearization is usually used in context of an application, and we're saying, I've got this function, it's very involved, it's got lots of interesting things going on, but I don't care about those interesting things. I want a linear approximation to that function. What is that? What does it look like? They gave you a complicated formula, or something that looked relatively complicated in Calculus 1, but really it was just a tangent line. It was something that you had been calculating for a long time. No big deal. Can you imagine what the Calc 3 version of that is? I hope you said tangent plane, because that's exactly what it is. So if we're talking about the linearization of z equals f of xy, linearization is just another name for the tangent plane. So you're going to solve the equation of the tangent plane for z. And then usually we replace it with this notation, L of xy, to say that this L of xy is a linear approximation So this is the linearization of z equals f of xy. It's a linear approximation to the surface. And of course they have to give you a particular x naught, y naught, because you're going to have different tangent planes at every point. So it's a linear approximation to the surface at x naught, y naught. That's the linearization. So we've already calculated tangent planes. Linearization is no different. We're just going to take the equation that we found, solve it for z, and we're going to call it a linearization. So we're just saying in this new context, we're thinking of this as a linear approximation to the surface. Now let's look at our cartoon picture of a general surface. So here's z equals f of xy. And we're at some point on the surface where it's nice and smooth. There are no folds in the surface, no sharp corners. And we get something like this. Well, this zooming in process that we did earlier in Calculus 1 can be done again. We zoom in and 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 we zoom in. And here's where I almost sound like a flat earther apologist. Eventually it looks flat. It looks like a plane. Just like eventually this looked like a line. Eventually we get so close that the surface and the plane, the tangent plane, are indistinguishable. We're saying, when somebody asks you for the linearization, they're like, what's the equation of that plane? How would I describe that? And so this linearization, it's just the tangent plane, but we're thinking of it as an approximation to the surface. It's the linear approximation to the surface at that point. So we're just saying, like, what does it look like when we get really, really close and we zoom in and we zoom in and we zoom in and it looks very flat, like we're flat earthers. It looks flat. What's the equation of that flat thing that it looks like? That's the linearization. So let's look at our last example with that horrible looking surface, horrible looking cartoon surface over here. This was the equation of the tangent plane. The linearization just comes from taking this and solving it for z. So I will subtract 4x from both sides, add 5y to both sides, and divide both sides by 7 to get z by itself, and then replace the z with L of xy. This is the linearization to this surface at that point. All I did was take this, solve for z, and replace z with L of xy. Now earlier, in a different video, we came up with this surface. We had an ellipsoid, and at that point, 1 square root of 11, 2, we found this tangent plane. Well, what's the linearization there? Well, first let's solve for z. So we'll subtract 9x and subtract square root of 11y from both sides, divide by 8. And you want to simplify wherever you can. 4 goes into 8 twice. 4 goes into 36 9 times. Now we're using z here. We don't want to use z because we're saving z for the z in this equation. So we're going to replace z with L of xy. This is a linear approximation to z at this point, 1 square root of 11, 2. the linearization of the surface at that point. Okay. Last example, this was also from the last video. We were right here. To find the linearization, we solve this for z. And we replace z with L of xy. So the linear approximation of this surface at this point is this. Okay, so let me write down the procedure for you, even though it was very simple. Actually, I've already done it. It's right there. You find the tangent plane, solve the equation of the tangent plane for z, and then you replace it, that's z, with L of xy. Again, the linearization and the tangent plane are just the same thing. We're just thinking of it differently. We're saying that's a linear approximation to the surface. If the surface was linear there, well, what would that look like? What would the equation look like? We're saying if you get very, very close and you zoom in and you zoom in and you zoom in and you zoom in, eventually the plane, the tangent plane and the surface itself are indistinguishable. What is the equation of that plane? That's what we're finding when we find linearization. Now, I promised you we'd do one more thing in this video. We're going to find the normal line to a surface as well. A normal line is actually very simple. It's just an equation, or it's just the equation of a line that is normal to the surface at a particular point. Well, if we already know the normal vector, and this one looks like it's parallel to k hat, but it shouldn't be. Then it's not a vector. This is the gradient of capital F evaluated at x naught, y naught, z naught. If you know the normal vector and you know a point on the surface, you just put those together to find the equation of the normal line. So let's write that down. Well, remember, a line has a direction vector. You need two things. You need a direction vector v, and you need a point on the line to distinguish it from all of the other lines that are parallel to v. So I'm going to write x naught, y naught, z naught because we're in three-dimensional space, but this could be in 2D or ND or however many dimensions you want. So that's what we need. We need a direction vector. If we're in 3 space, it has to have 3 components, and we need a point. Well, we're talking about the line that is normal to the surface. If the line is normal to the surface, the direction vector is a normal vector. And the normal vector can be the gradient of capital F, evaluated at x naught, y naught, z naught, or you can multiply it by any constant you want to make the coefficients as simple as possible. And x naught, y naught, z naught will be given to you. So in our earlier example, we had x squared y cubed minus y squared z plus 2xz cubed equals 4, and we found the tangent plane at x naught, y naught, z naught equals -1, 1, -1. Well, that's our x naught, y naught, z naught that we need for the equation of a line. We also need the direction vector of the line, but the direction vector and the normal vector of the tangent plane are the same when you're talking about the normal line to a surface. It's a line that passes through this point that is running parallel to the normal vector of the plane. So earlier we calculated this. The gradient of capital F at this point was -4, 5, -7. Okay, so you could use that as your normal vector. I multiplied it by -1 because I wanted that x-coordinate to be positive. So I said, let's take the negative of that. The normal vector and the direction vector of the normal line are the normal vector to the plane, and the direction vector of the line are the same thing. So this is your ABC. Now remember what we did with lines. We have parametric equations. X of t is x naught plus at. Y of t is y naught plus bt. And z of t is z naught plus ct. And all we do is we substitute the a, b, and c, the x naught, y naught, and z naught. And that's it. Those are the parametric equations of the line. X naught, y naught, z naught is -1, 1, -1. A, b, and c are 4, -5, and -7. I think that's wrong. That was negative, so multiplied by -1, that should be +7. 4, -5, and +7. So those are our parametric equations of the normal line. If we want the vector equation of the normal line, we just use a vector valued function r of t with components x of t, y of t, and z of t, and you substitute the parametric equations in over here. So we've got -1 plus 4t, 1 minus 5t, and -1 plus 7t are the components of r of t. So this is the vector equation of the normal line. Easy breezy. If you've already found the tangent plane, you already have the normal line. So you just have to, or you have all the things you need for the normal line. You just have to remember how to put those pieces together to get a line again. So those are the formulas for the parametric equations. And again, the vector equation, just take the parametric equations and sub them in as the components of your vector valued function over here.